Good evening, everyone. Thank you for joining us tonight. Welcome to the Avexia webinar series. Our topic for tonight's special webinar is Oxidative Stress Using Blood Chemistry. Who needs antioxidants and who doesn't? My name is Joanne Iverson. I am the Director of Client Relations for Avexia Diagnostics and will be your host for this evening. Tonight, I have the distinct pleasure of being joined by an exciting guest, Dr. Bryan Walsh, who will be our presenter for this webinar. Dr. Bryan Walsh has been studying human physiology and nutrition for over 25 years and has been educating others in health for over 20 of those years. When he isn't teaching, he spends his time poring over the latest research and synthesizing his findings into practical information for health practitioners to use with their clients. He has lectured to members of the healthcare industry around the world and consistently receives positive feedback in his seminars and courses. His online educational platform, Metabolic Fitness, he helps health professionals to stop guessing and start knowing what to do with their patients. While Dr. Walsh is known for his expertise in biochemistry and human physiology and his unparalleled ability to educate on these topics, he is perhaps best known for challenging traditional dogma in health and nutrition concepts, such as questioning current models of adrenal fatigue, glucose regulation, detoxification, mitochondrial dysfunction, and more. As such, he has been sought out to consult with multiple companies, academic institutions, and wellness organizations. Dr. Walsh is also a board-certified naturopathic doctor and has been seeing patients throughout the U.S. for over a decade. Joining Dr. Walsh tonight will be Dr. Wayne Sedano, our Director of Clinical Support and Education at Avexia Diagnostics. Additionally, Dr. Sedano is the Director of Integrative Medicine Education for the College of Integrative Medicine and lectures and teaches internationally. Before we begin, just a bit of housekeeping. We encourage participation. So if you have a question, you may submit your questions in the questions field in the right-hand area of the interface. We will answer submitted questions towards the end of this presentation. If your questions are not answered this evening, you will surely receive an answer by email within a day or two. In addition, there's also the downloadable slides that you should be able to see under the handout section. If you want to go ahead and download those, or you'll be able to use those as well. Without further delay, I will now turn the webinar over to Dr. Walsh.
Great, thanks, Joanne. Appreciate that. Thanks for that intro there. This slide is a little bit about myself, but it's redundant since you just said some of those things. I just want to let people know who I am if you haven't heard about me. I go for God first, and then I cherish my wife, and I have 6 children with her. And this is what I spend most of my life on, is those 3 things there. The rest of the time, I'm a naturopathic doctor, and I really like trying to figure out the body, how it works, and trying to integrate nutritional and natural medicine practices into it. The Chief Medical Officer in Metabolic Fitness, the company that my wife and I have together, where we're trying to raise the bar in the functional medicine industry through education. I put together what I consider to be the first truly evidence-based from the scientific literature optimal reference ranges in blood chemistry. I'll show you a few of those markers tonight. And as you said, I constantly challenge the popular narrative in the industry. I like to think about things and then like to do some research on it and then some investigation. And I find many times that the common story or narrative that is being told isn't always necessarily the right one. And if there's anything that anybody wants to take away from this, I want to just say, if we've been wrong in the past, and we have many, many times, what makes us so sure we're right today? And in general, my wife and I try to encourage less protocol-driven thinking and more critical thinking. So here's just big picture where I'm going to go. I'm going to summarize it before I get started. I tend to go quickly. I know this is recorded. We can go back and listen to it later. We're going to be talking about oxidative stress. So oxidative stress is real and it exists. I do think that in general, we know a lot less about it than we think we do. And I am not the one that came up with that. I study people who have been looking at redox biology for 50 years, for multiple decades, who've changed their mind about things that as they've progressed, they're now 70 and 80 years old. They're brilliant in this subject. And I do think we know a lot less than we think we do. However, oxidative stress is associated with just about every chronic condition. So there's something to it. And then therefore, and when you look at studies on antioxidants, it doesn't seem like it's a great idea to be giving them without some kind of justification. So then the question becomes, how do you assess that? Who needs which antioxidants and when? And then when you look at the assessments for oxidative stress, when you really look at the scientific literature carefully, and I'll show you a bunch of these papers tonight, much of this is not my opinion, by the way. I'm just the deliverer of the mail, so to speak. That the assessments leave a lot to be desired. I will just say that, and I'm going to show you the evidence for that, which then leads to the question, should we be giving antioxidants or not? Do we have anything in the scientific literature that we can say as functional medicine and nutritional practitioners, I have evidence-based markers that evaluate oxidative stress in my patients and clients today? And the answer to that is yes. There are 3 that we'll be going over. They're very inexpensive. The literature is there. And until proven otherwise, these offer some of the best, most inexpensive screening tests for oxidative stress. And at the very end, I'll show you some evidence-based therapeutic interventions that we can use for each of these markers, or at least 2 of them. All right, so I said everything in the entire presentation, but let's see what I actually said. So oxidative stress is real and it does exist. However, like I said, we don't know as much as we think we do, but it is associated with just about every chronic condition that's out there. The random unjustified use of antioxidants in human clinical trials has been disappointing and sometimes even dangerous. And I think that's because this is not the it just steals an electron off of a protein or a fat and it unfolds the protein or it oxidizes the fats. It's not that simple. It's incredibly complex. And I do think we know far less than we think we do about it. So it turns out, and I'll allude to some of this. Remember, this is a 1 to 2 hour presentation. There's no way we can cover all of this. But too much or too little oxidative stress can be detrimental. So we don't want to just, and the studies are clear on that, we don't want to just start giving random amounts of antioxidants to anybody. We want to give it the right ones to who needs them and have some justification for that. Yet, as you will see, accurately assessing oxidative stress is really difficult. It's a lot more difficult than some make it out to believe. So then the questions become, how do we know who needs them and not, and who doesn't? As well as which ones, fat-soluble, water-soluble, which patients need to be tested for issues with oxidative stress, and can we inexpensively and accurately assess patients using truly evidence-based from the scientific literature, not petri dish studies, not mouse studies, information from the scientific literature. So there's 2 main things we're going to be doing, and the first one is we're going to talk about problems with assessment. Okay. Now, so this is going to cover, and I know I go quickly. I'll slow down when there's a real big point that I want to try to make. There are problems with oxidative stress assessment, and I'm going to show you just a smattering of the papers. I show you the paper. I take quotes directly out of the paper so that you can investigate this yourself. I always tell people, do not take my word for it. I'm showing you the literature that I have found and encourage you to go through it and read it yourself and come up with your own conclusions about it. Again, we're trying to make critical thinkers and not just people that parrot back what other people say. So here's some of the stuff that I found. First of all, you're probably familiar with the urinary organic acid marker, pyroglutamic acid. It's also called 5-oxyproline, depending on the lab. And this is a marker, when you look at the glutathione cycle, that when it's elevated is an indication of low glutathione. And biochemically, that makes a lot of sense. And I think that it's a pretty accurate marker for that. However, here's a paper that shows what they did was they took a number of healthy subjects. They did a urinary sample once a week for 8 weeks. They looked at a whole bunch of markers, and this particular paper talked about pyroglutamic acid. And the first thing I want to show you is, so we're running this marker in urinary organic acid tests and looking at high pyroglutamic acid and suggesting that that patient, depending on their level, might need glutathione support. Maybe it's N-acetylcysteine or more vitamin C or whey protein or glutathione itself. But that's usually how it's used. But if you take a look at the study, they narrowed it down into what they called low variance subjects and high variance subjects. The low variance subjects, you can see here that by and large had pretty tight over that 8-week period of time. These down here in the x-axis are the different participants, male and female. And it was pretty tight that their pyroglutamic acid never really went to, there was some variance, as you can see, which makes sense, but there wasn't too much variance. Now down here on this bottom one, you can see that in these ones, they called these people the high variance subjects because there was obviously more variance in their pyroglutamic acid over that 8-week period. Now, this is important because I ask, what if, and just take any one of these people, say, let's say that this is the day here that you saw them, and this is the day that they ran their urinary organic acid, and this is the day that they got their pyroglutamic acid run, and you said, wow, you have a lot of oxidative stress. you need glutathione. But if you watch over the rest of those 8 weeks, they kind of took care of themselves without any interventions. And so there's some variance to this. And then the first question should become, well, when am I running their lab? Let's say you ran their lab and it's down here. You look good, no oxidative stress, no need for glutathione. Yet they're at a different point in the past couple of months might have needed it. Now, here's what's really interesting, and this paper talks about, is when you look at these patterns in these people, it's really remarkable how similar it is. And the suggestion is, and ready for this, that, and this makes sense, that when there is a higher need for glutathione, pyroglutamic might go up. But then the body's response to that, in knowing that there's excess oxidative stress and a higher need for glutathione, ramps up their glutathione synthesis pathways so that you make more glutathione, less pyroglutamic acid, and then happy antioxidant, or let's just call it redox balance. But so then the question becomes, is this a good marker of oxidative stress? And I would submit that just based on this, no. If there's a chance, biochemically it makes sense, but if there's any variance to this, then you don't know when this person needs antioxidant support, or if you grab them on the wrong day, you might be recommending something that if they were left alone might be taking care of themselves, unless you ran serial testing on them and you might have a better idea. This is another really cool paper. Check the title of this one out. Prediction of autoimmune disease by targeted metabolomic assays of urinary organic acids. Sounds awesome. Now, what they did is they were basically trying to find what patterns in an organic acid test an autoimmune disease patient might have versus a healthy control. And there's a whole bunch of ones here. And like I said, it's kind of an interesting paper. You can look through it when you get a chance. We're told, and I've heard this in the industry many times, that if you have an autoimmune patient, that you need to load them up with glutathione, rub it on them and drop it in their mouth and nanoparticles or whatever kind of glutathione you want, but they need glutathione. But yet, remember, high pyroglutamic acids just suggest the glutathione need. Yet, when you look at this, it's not a huge difference, although it reached statistical significance, that the autoimmune group actually had lower pyroglutamic acid than did the control group that had slightly higher glutamic acid. Now, again, this is not a huge fluctuation in between the two, but we're told that autoimmune patients they have a need for glutathione. Based on what? Well, not based on this. So we need to be careful when we hear things like that, because at least according to this paper, they didn't have low glutathione and didn't need it. So here's, let's keep on looking at this. So this was a really cool paper, and I don't usually put the subheading, but this subheading was really creative. Redox analysis, they called it a hitchhiker's guide to assessing oxidative damage and redox signaling. Now remember, big picture, what we're talking about right now is problems with oxidative stress assessment. Now, what they say in this paper is that redox analysis is extremely difficult because the half-life of most reactive species is milliseconds, and even nitric oxide, a relatively stable species, is consumed within about 2 seconds. Now that makes sense. How are you going to test something that's in and out that quickly? And they said that there's considerations are fivefold regarding assessing oxidative damage and redox signaling. So you can't measure the reactive species themselves, but now they're going to talk about these 5 different things to consider when it comes to looking at oxidative damage and redox signaling. Number 1, markers of macromolecule damage lack exclusivity. That means it could come from a variety of different places in the body. Oxidized macromolecules are subject to repair, which is kind of what we saw in that pyroglutamic acid one. Not exactly, but what we're looking at is damage, but there's a certain amount of repair that's also taking place. Global levels, systemic levels of macromolecule adducts are unable to report on redox signaling because the two are mechanically different. Optimal sampling time varies, I'll just say that. And redox biomarkers can exhibit a circadian oscillation. Well, we just saw that with the pyroglutamic acid. It circulates or oscillates in certain people over a period of weeks, but they're suggesting that there's also some variance even throughout the day. And as you'll even see in a second, it might even be seasonal. Okay? They go on to say that there are certain assays that are flawed and should be abandoned. I mean, they don't mince words about this. They said these should be abandoned. And this isn't the only paper that says this. The T-bars, which is used in assay to look at lipid peroxidation, is no longer recommended. One of the reasons why is this malondialdehyde, which isn't a bad marker of lipid peroxidation, but they say that normally you need 2 or more indices, and I agree, are necessary to confirm lipid damage. And then they also say that this total antioxidant capacity is equally flawed and should be discontinued. Now, this is not the only paper that suggests this. There's a number of papers that do as well. Now, take a look at this paper before I go on with this. And you look at the number of authors. There's 140 authors that were on this paper that took 4 years to write. And notice the title, plain and simple, redox biology. Okay, it's I think it's 73 pages. It's either 73 or 79 pages. It is very comprehensive. It is very complex. It took 4 years to write and 140 people to write it. And if it's me, I'll probably put a little bit more value to this if it has, first of all, a table of contents. Any paper that has a table of contents is awesome. That you're going to spend a little bit more credibility if you have this many people that's working on this. So let's look at it. We're going to come back to this paper a couple of times because it was long and they said a lot. But let's look at what they said about we're still looking at, can we accurately assess redox biology, oxidative stress markers? In this paper, part of what they said was, the current review has included some indications as to how oxidative stress biomarkers assays may be applied to medical research studies. Now, what they just said in English was, and this paper looks at a whole mess of biomarkers. They were looking at how they can use it in medical research studies. That's fine. But look at how they finished the sentence. But the demonstrated clinical value of oxidative stress measurements in diagnosis or monitoring patients has so far been disappointing. Now, I'm just going to take a step back and say really quickly, there are things that work in the scientific literature when it comes to studies. For example, things that are representative are really effective in populations. So hair tissue mineral analysis, phenomenal in identifying a toxicity or deficiency in a large group of people. If you have a city or a state or a country and you want to find out if they're mercury toxic or lead toxic or arsenic, or maybe they're magnesium deficient or selenium deficient or copper, hair tissue mineral analysis, fantastic. On an individual clinical basis, the literature is very clear. It is not accurate for that stuff. That's because you're taking averages of populations. Same deal here. What they said was we have been looking at all these different ways of assessing oxidative stress for medical research purposes, but in a clinical practice, it's been so far disappointing. So here's a paper. Now, watch, this is just by one guy, you can see. But he says, oxidative stress, what is it? Can it be measured? Where is it located? Can it be good? Can it be bad? Can it be prevented or can it be cured? Very good paper, by the way. So take a look, just a quick screenshot in your brain of all the different things, and you'll probably recognize some of these markers. You have, here's a couple of DNA markers, usually sometimes ran in the urine, glutathione assays. Here's lipid peroxidation, malondialdehyde is on here, oxidated cholesterol particles, we'll just say myoperoxidase, probably familiar with advanced glycated end products. So there's a whole bunch. He just listed them all out. Now, the next thing he says is relating to these, and here he goes. He says, essentially, the above static techniques, go back to the previous slide, all those things, is what he's talking about, do not measure oxidative stress, which is a dynamic concept, and I love that. Other techniques have also been proposed to measure the molecules that cause damage, and here he is agreeing with that other paper, reactive oxygen species, reactive nitrogen species, hydrogen peroxide, and nitric oxide. These measurements have the drawback that the molecules in question are subject to rapid and uncontrolled decay. What he said is they're in, they're out, they're too fast, you can't measure them. He goes on to say, attempts are made to measure the antioxidant function of enzymes, right? Now this makes sense too, because here, let's take a step back. You can measure the reactive species, which you can't because it's too fast. You can measure the damage, which is possible, but as you saw in that previous one, there's a lot of drawbacks to that. Or you can measure the antioxidant enzymes. Okay, so those are really the three big ways of trying to evaluate oxidative stress. Reactive species, too quick, can't do it. Now he says attempts are made to measure antioxidant functions of enzymes, such as catalase, glutathione, superoxide dismutase, or complex mixtures like ORAC, everybody loves that, the HORAC, hydroxyl radical antioxidant capacity, or the total antioxidant capacity. And he says of these, all these techniques have strongly been criticized. Now, again, I have personally spoken with individuals, brilliant individuals in this single subject area who have been studying it for decades, 70-year-old Italian guys, for example, that know everything about this subject. And this is the general consensus that these are really, it's really hard to evaluate and assess. Therefore, the question is this is a smattering of the literature, there's a lot more out there, but are there problems with antioxidant, oxidative stress, redox biology assessment? And the answer is yes. Okay? This again, in the interest of time, there's a lot more that I've done with this in the past, but there are problems with it. So then the question is all right, well, if we can't assess it really well, should we be randomly giving antioxidants? And there's a couple of points that we're going to cover here. One is when you look at human clinical trials, most of them don't support exogenous antioxidant therapy. Now, there's some caveats to that, and I'll explain this, which is really kind of funny, actually. So there's the old oxidative stress view, free radical view of aging. And because there was long-lived animals seem to have a lot of antioxidants. So we said, all right, what happens if we increase antioxidants in humans? And it didn't, or large mammals, and it didn't really seem to do much for longevity or even helping with aging. So we were wrong there. And here's a recent paper that said up till now, there's been no prospective clinical intervention studies that have been able to show a positive association between antioxidant supplementation and increased survival, which is longevity. They go on to say that antioxidant supplements do not possess preventative effects and may be harmful. This is really good, especially to us in this industry, with unwanted consequences to our health, especially in well-nourished populations. And I'll be real honest with you. I was talking to my wife about this recently. I think that those that are in the functional medicine and nutritional industry probably contribute, 70% of the money that goes into that industry in buying supplements. It's, we have to convince patients to take them, but we ourselves usually have bucket loads, and are running the tests on ourselves. And anyhow, so this paper was interesting. And again, I showed the paper to you so that you can check it out yourself. But this was interesting because they were talking about and they were reviewing other studies that have been done and suggest that in the well-nourished populations, exogenous antioxidants may actually have a detrimental effect, unlike somebody who has some kind of chronic disease, which you can make an argument for. And in a while, I will show you some markers that you can look at in these people. Back to this paper of 140 authors, it took 4 years to do. They suggested regarding taking antioxidants, most large-scale antioxidant clinical trials yielded disappointing results regarding all-cause mortality, and some cases, oral antioxidants had detrimental effects. There it is again. And listen, this is kind of an important piece, this last part of the sentence. And to this date, no antioxidant is admitted as a drug for clinical use at the time of this writing. And this paper is, I think, 4 years old. But think about that for a second. If the pharmaceutical industry could make money off of a drug, you know darn well they would. Okay, and I'm not bashing, I don't bash people or industries. If I'm going to, it'll be equal opportunity. But you know that the pharmaceutical industry has a history. If they can make money off of something, they absolutely will. Why has no antioxidant? And it's not because it's natural. They can synthesize all sorts of really cool antioxidants that you don't find in nature necessarily. Synthesize, isolate, but it's never been admitted for clinical use. Wonder why? Okay, it's very interesting. Seems so simple too. They go on to say chronic systemic oral therapy with antioxidants will likely, and this is the biggest, the coolest part of this, will interfere with important reactive oxygen species mediated cellular processes. Okay. I only have a little bit in this presentation on this subject, but man, this is a very cool subject. I've covered it in depth elsewhere, but this is a cool subject, which I'll be getting into now. That is because it turns out some oxidants are critically important signaling molecules. And this was kind of a game changer when all of a sudden hydrogen peroxide was not just this intermediate step between hydroxyl radicals and water, but in fact was a signaling molecule. And just to kind of give some context for this, neurotransmitters are signaling molecules. Hormones could be classified as signaling molecules. Eicosanoids could be signaling molecules, right? So this now is not, like I said, if you remember turning hydroxyl radical into water and all the steps that are required for that, and the enzymes and antioxidants, hydrogen peroxide is an intermediate step in there and is said to be kind of a byproduct. It comes out of the mitochondria, for example, in sort of a lot. And if you paid attention, or actually what's coming up, you'll see xanthine oxidase. When it turns purine nucleotides into uric acid, it too produces hydrogen peroxide. So we used to think, well, hydrogen peroxide is just this intermediate product. It's not. It is a critically important signaling molecule that I'll just touch upon in just a second. Anyhow, if we take antioxidants unnecessarily, are we potentially blocking the signaling portion of these? Okay, it's very interesting. Here's back to the same paper again, because they had a lot to say. So check this out. Nitric oxide synthase, xanthine oxidases, which I just mentioned, lipoxygenases, cyclooxygenases, cytochrome P450s, peroxidases, reactive oxygen species in the mitochondria play various roles in the cellular signaling network under different physiological and pathological conditions. They go on to say, various cellular antioxidant systems, okay, glutathione, throw in your favorite antioxidant, oppose the reactive oxygen species load, thereby limiting not only cellular damage, they do that, but also contribute to reactive oxygen species dependent signaling. This is the part that I said becomes very complex. So it's not just causing damage to proteins and stealing the electron because it's a hungry little free radical, and now the protein is lacking an electron and it can't hold itself together properly and it's oxidized. This is suggesting that this redox biology, antioxidant, pro-oxidants, that it not only causes cell damage, but has to do with cell signaling, which, if you think about it, the signal has to be just right. Kind of like the three little pigs until I have 6 kids. If there's too much or too little, it's a problem, but there's a sweet spot in the middle. And if you have too much signaling, that's a problem. If you have too little signaling, that's a problem. So remember, now if we go back to those high variance subjects in that pyroglutamic acid study, you can see that that variance maybe was on purpose by the body. And if we start messing with that, what are we actually messing with? In a parenthetical note, this is a side note which we're not talking about. I will come back to this later, but I wanted to include this. This paper said bacteria and toxins are important stimulators of cellular reactive oxygen nitrogen species formation. So they are admitting that we can have too much, but these two things, if you think this is a real conventional paper, think again, because they're talking about toxins and environmental pollutants and bacteria as stimulators of this. So things to consider. Now, this is a really important paper. I went into great detail on this. I have about an hour-long presentation I think I did on this. But lest you think maybe we shouldn't, maybe we're giving things that we shouldn't. I'll put it this way, and I'll show you what this paper says. Is it possible? Well, here, have you ever been told that if you have poor T4 to T3 conversion that you need to give selenium? I've seen that for decades in this industry. And I will tell you, for a variety of reasons, I'll summarize it here, that's a bad idea. There are no or very limited studies, and I have a good couple dozen of them, suggesting that low selenium is going to cause, that giving selenium is going to increase conversion of T4 to T3. And there's a whole variety of reasons for this. But I did interview at one point this very old Italian researcher, and I said to him something about thyroid conversion, and he basically said, if you couldn't convert T4 to T3 because of selenium deficiency, you'd basically be dead, because the deiodinase enzymes, there are certain enzymes in the body that are the last ones to give up selenium, and you have to be so low for them to be impacted in a negative way that you would have other problems. Let's put it that way. So check this out. This should make you think twice about giving anything to anybody, but selenium especially. Evidence shows that adequate concentrations of selenium, ready, play a key role in the secretion and action of insulin. Let's just stop right there. You need selenium to be able to make insulin and have it work properly. Great. But an excess of selenium in the body is associated with the pathogenesis, you know what that means, the causation of insulin resistance and the development of diabetes, type 2 diabetes. So wait a minute. What that just said was you need some selenium to make and have insulin work properly, but too much actually causes the thing that you're trying to prevent by making sure someone has enough selenium. They go on. It has been emphasized that chronic ingestion of large amounts of selenium promotes the formation of antioxidant selenoproteins. So let's just stop there. What they're saying is what I just suggested, that if we take too many antioxidants, that we are not, first of all, most antioxidants can become pro-oxidants, and there's only one true antioxidant supposedly from a free radical perspective, and that's vitamin E. Most of the other ones, just as a side note, most of the other ones act as antioxidants and then stimulate antioxidant defenses like NRF2. But what this is saying is, if you give the body too much of this, though it's pretty tightly regulated, that you can make too many antioxidant selenoproteins, and that's going to impact the signaling, and that's going to cause insulin resistance intracellularly with too much selenium, leading to the reduced concentration of reactive oxygen species like hydrogen peroxide, which are required, ready? Look what it says. Certain amounts of reactive oxygen species are required in physiological amounts for insulin signaling. And if I were just to take a pause right here and to say, where have we been so far? What are we talking about? We're halfway through. Wow, it's amazing. What I started out with is oxidative stress is real. Okay, too much and too little is bad. We need to kind of be in the sweet spot. Therefore, we want to say, well, let's assess people on this. And what I showed you was, according to most of the literature in this space, that assessment of it is very, very difficult. It's a very complex subject, and assessing it properly is difficult. Then I went on to say, so then if assessment is difficult, then why don't we just give antioxidants to people? Well, the literature is fairly clear on that as well, that maybe that's not necessarily a good idea, and in some cases might actually be detrimental. And what this is now saying is that it can cause issues with cell signaling and cause insulin resistance. The same paper goes on to say, now ready? If that wasn't enough, when ingesting selenium in sufficient amounts to maintain plasma concentrations in the range of about 80 to 120 micrograms per liter, selenium acts as an antioxidant and insulin mimetic nutrient. That's good, favoring the synthesis and action of insulin. But ready? However, when selenium intake results in plasma levels above 120 micrograms per liter, the cellular redox state may become dysregulated. That's the signaling of hydrogen peroxide, for example, which can compromise the chemical interactions involved in the insulin signaling cascade, which is to say, too much selenium taken exogenously in any way, even in Brazil nuts, can contribute to insulin resistance and eventual type 2 diabetes. Okay? So this is just a thought. Now, I've tried to present the literature and evidence as best as I can. This is me just thinking out loud and very bold, so very out loud. But might the issues with oxidative stress be caused by cell signaling and not cellular damage? And it's something that I postulate about. Some stuff in the literature, but something to think about. So then the question coming back to this was, remember the first thing we said was, is there a problem with assessing oxidative stress? And yes, there is. Again, the literature is super clear in this. Experts that, you know, the kind of experts that if you could have, when people say like, what 3 people could you have over here to dinner? It'd be one of these people. They're so incredibly smart in this one subject that you could just download so much. It'd be I mean, maybe a boring dinner, but man, you'd learn so much information. Decades of research in this subject, and they say that it's almost impossible to do to assess this. So I personally say no. I don't think we should be giving antioxidants randomly to people. So then part 3 of this webinar is basically, wouldn't it be great if we had inexpensive, evidence-based way of screening different types of oxidative stress in patients? And the short answer is that according to the scientific literature, we do. There's serum uric acid, serum GGT, and serum bilirubin. I will tell you, if you use all of these together, it tells you more than just one of them. However, as sort of a little prelude is where we're going. Uric acid is fascinating. If it's high, it can indicate oxidative stress, but the body is winning. If it's low, it can indicate oxidative stress and the body is losing. And I will tell you that in terms of interventions of increasing low uric acid, I haven't been real successful in finding them. However, as you will see with GGT and bilirubin, one of these looks at water-soluble oxidative stress, specifically glutathione, and the other one looks at fat-soluble oxidative stress. So when you consider all these 3 things together, we have right here a great oxidative stress panel that's backed up in the literature. And with GGT and bilirubin, I will show you evidence-based interventions that you can use specifically with doses in order to help correct what might be causing these to be abnormal. All right, so let's get started. I can't see any comments, but I'll just go ahead and ask if everybody's doing okay. Hopefully everybody's doing all right. Okay, so uric acid, a little bit of physiology review because it's fascinating and fun, and I like to throw in a little bit of physiology trivia. If you ever end up at a physiology party of some kind, you can drop some of these trivia nuggets. But then we'll talk a little bit, we'll look at the evidence of it as a marker of oxidative stress. So, as I said earlier, it's a major end product of DNA purine-based metabolism, specifically adenosine and guanosine. And you can see here that eventually either one of these turns into hypoxanthine, then xanthine, then uric acid. We have the same enzyme twice, xanthine oxidase. Here's that hydrogen peroxide that's made. Interestingly enough, perhaps that's a signaling molecule here. It is a molybdenum-dependent enzyme, but not just that. You also, if you see down here, you need iron in order to be able to reduce, or I should say oxidize molybdenum. And then down here, you also have FAD, which is the active form of B2. So really, when people say it's a molybdenum-dependent enzyme, they're not wrong. However, you also need iron and a little bit of B2 in order for this process to be able to work. Which, by the way, if you remember the introduction, I said what I like to do is have critical thinkers. So using this information, what might someone's serum uric acid be if they were iron deficient? It would be low, as you can see. If you don't have enough iron, you can't oxidize molybdenum so that you can reduce molybdenum through xanthine oxidase. Okay. Riboflavin's probably not low. Once again, if riboflavin was low enough to cause issues in this pathway, you'd have other issues. So, okay, how much do we make? It mostly is made in the liver and the intestinal mucosa, which is very interesting to know. We make about 700 milligrams a day. It's going to vary quite a bit, however, because dietary sources of nucleoproteins that are going to contribute to that breakdown is about 300 milligrams per day. But listen, in this industry, we have people choking down oysters and liver, and we have vegans. So they have a considerably different amount of these nucleoproteins when they eat it. And so they will be making a lot different levels of uric acid. It is excreted via the kidneys. Very interesting how. Again, it's going to vary the amount. So here's a couple things to know. And I mentioned that there's some seasonal variance to some markers. Day-to-day and seasonal variations in uric acid tends to be higher in the summer than in the winter. Now here, I'll slow down on this because this is a little pearl. When there's alkaline urine, there tends to be more excretion of uric acid. And if there's acidic urine, and this is probably what we see more often, there tends to be more reabsorption. So if it's, and you know how the kidneys work, it filters, well, I shouldn't say it. Yeah, it filters and then reabsorbs, right? And excretes or secretes. There's 4 different things the kidneys do. So it filters uric acid into the, let's just say the collecting ducts, the tubules and nephrons. And then some of it gets reabsorbed, or it can be excreted. When it's in those tubules, it can be reabsorbed or excreted. Under acidic urine conditions, it tends to be more reabsorbed, which means then where's it getting reabsorbed to? Back in the system. So if somebody has high or high normal uric acid, one of the possibilities is that they have acidic urine. And merely, I don't like to use the term alkalize their urine because there's a variety of ways of doing that. Less protein, more vegetables, sodium bicarbonate, potassium bicarbonate. If you alkalize them a little bit and their urine becomes more alkaline, you have the opportunity to see uric acid actually go down. However, we're not done. We're just getting started with uric acid. Uric acid has been associated with increases in exercise stress, weight, hypertension, diabetes, cardiovascular disease, a whole bunch of things, even type A personalities. And while that may sound interesting, when you consider that type A personalities are generally stressed in general and could be more prone to hypertension, then it kind of makes sense. There's some older Russian papers I saw that talk about this. They're associated with higher levels of uric acid. The jury is still out as to uric acid, if it's good or it's bad. There's some people that suggest that higher levels are better with cognition, which is interesting. I'll show you a paper in a second that temporary high levels seem to be protective, but long-term seem to be damaging. Actually, I'll just say this. I don't even have it on here. Uric acid is the most abundant extracellular antioxidant in the body. I'll say it again. I didn't say it's the most potent. Uric acid is the most abundant extracellular antioxidant in the body. Newer research suggests that uric acid can be a marker of oxidative stress and act as an antioxidant or reducing agent, but if it can act as an antioxidant, there's really strong suggestions that uric acid can also act as a pro-oxidant, intracellularly, by the way. And remember, if we're measuring the serum, that's extracellular. Similar to other reducing agents like vitamin C, uric acid can also act as a pro-oxidant. And of course, uric acid is associated, when it's high, with all sorts of different conditions. And there's some debate I have here as to whether high uric acid is causative or correlative, but I'll show you a paper that suggests that it's correlative, and at least when it comes to the heart, may not cause damage to the heart. And this one here, in fact. So in this paper here was looking at uric acid and chronic heart failure. The totality of experimental and clinical evidence supports the premise that uric acid is not injurious to the heart. So it's not causative, it might be correlative, but instead is a biomarker of oxidative stress. And that's why we're here. We want inexpensive, scientifically validated evidence-based from the literature with reference ranges, which are coming, markers that we can screen for oxidative stress in our patients. And uric acid is a really cool marker to be able to do this. And I'll tell you how. Here's a paper that I was explaining to you. So if you're ever interested in looking at uric acid and neurology, there's a lot out there, and it's very interesting. It's not really conclusive at the moment, but it is very interesting. And this paper talks about cognitive dysfunction. Again, uric acid has been suggested to be beneficial towards cognition, but this paper is saying it is a time-based thing. So based on the results of experimental and clinical studies, uric acid seems to play a dual role as a pro and antioxidant. They go on to say that taking these lines of evidence together, uric acid appears to exert a protective effect on brain tissue. However, during the initial stage of elevated uric acid levels, primarily because it's an antioxidant. But long-term elevation appears to trigger an inflammatory response that leads to brain tissue damage. This paper was looking at serum uric acid levels and correlating that with salivary antioxidant capacity. And what they found, we're talking about uric acid as a marker of oxidative stress. That's really what we're after. We could talk about other things, but let's just stick with this. So we found there was a marked decrease in, now we're talking low serum uric acid levels caused a decrease in serum and saliva antioxidant capacity and an increase in oxidative stress. And this is the point that I'm getting to. Low uric acid is a marker of oxidative stress that the body is not coping well with. And you see this here. Low serum uric acid levels was associated with an increase in oxidative stress. And it says it here, it's possible that an increase in uric acid concentration is a protective mechanism. It's a good thing because it's an antioxidant and your body maybe wants more of that antioxidant. Here, you want another clinical pearl while I'm at it? HDL, high density lipoprotein. One of its jobs is to clean up is kind of an arbitrary word, is to bind to lipopolysaccharides, systemic lipopolysaccharides, HDL, the good cholesterol. One of its jobs is to deal with lipopolysaccharides. And so it's no wonder that there's a study showing that men who had leaky gut had a higher level of HDL. Their HDL level was positively associated with their level of leaky gut. That makes sense. Intestinal permeability, lipopolysaccharides, more HDL to deal with it. High uric acid may be the body's attempt at making more antioxidants to deal with the oxidative stress that's occurring. If uric acid is low, however, that means that the body, for some reason, can't or is unable to. Maybe it's molybdenum, maybe it's iron, maybe it's something else, but it's not doing a very good job. So you'll see that in a second. So in fact, right here, look at all these studies on uric acid and a variety of different markers, and it's usually low. Low uric acid was associated with worse Parkinsonian symptoms. Low uric acid had worse mortality in dialysis patients. This paper showed that grip strength, which is a marker of vitality, if you will, was positively associated with uric acid. That means low uric acid, low grip strength. Low uric acid had worse prognosis of ALS. Here's another one, was a positive association with bone density. Higher uric acid, better bone density. Lower uric acid, lower bone density. There's another autoimmune case, low uric acid, higher myasthenia gravis symptoms. You guys can see the correlations with these. So elevated uric acid may indicate oxidative stress, but the body's attempt at dealing with it. So is high uric acid good? Not necessarily, but it's when it's low. This is when it indicates unchecked oxidative stress and is generally an indication of something bigger going on. You can see the title of this paper, the uric acid, the antioxidant paradox. And down here it says, well, one explanation for this paradox could be that a rise in uric acid represents an attempted protective response by the host, which is just what we've been saying. We review the evidence that uric acid may function either as an antioxidant in the plasma or a pro-oxidant inside of the cell. I'm not able to take quizzes here. But my question to you is, why would uric acid leave the plasma and go into a cell? I'll answer that in just a second. Here's a little tip for you too, based on that same paper. Ready? This is a big one. You need ascorbic acid to make uric acid act as an antioxidant. I'll say that again. Now, most people aren't really that deficient in vitamin C. We're talking like scurvy levels. But you need ascorbic acid in the plasma to make uric acid act as an antioxidant. It's kind of a big deal. But it doesn't scavenge against everything else, which is why we're going to look at other markers. And here was, so older papers, I'll say, and this is 93. I mean, what am I saying is actually old here. They did a cool job with some of this stuff. And I'll just summarize this. Ready? They took 10 healthy people. They took their uric acid level and glutathione, and then they had them jump in really cold water and then get out and then tested them again. And what they found was, this is awesome. They found that the uric acid went down really quickly. And the thought was, and here they say it, a drastic decrease in plasmic uric acid was observed during and following exposure. And they said that uric acid decrease can be caused by its consumption. So that would make sense. If it's an antioxidant and the body didn't have a chance to upregulate the production of uric acid temporarily when there was this burst of oxidative stress because they jumped in really cold water, then you would see a decrease in that. So this is another example. If uric acid is low, that generally is problematic because it's being used up as an antioxidant. You can't see it anymore as uric acid. All right. So I have a little asterisk here. Here's a traditional reference range, and here's an optimal reference range. Now, these are reference ranges that I came up with, and I have an asterisk here to tell you that my personal optimal reference ranges came from the scientific literature. I didn't make them up. I know that there are ranges in the industry that have circulated around, and some of them might have a reference or not. I generally have about a half dozen papers for each marker, and with those papers, I try to come up with a reference range that I think makes the most sense based on those papers, not something that I make up that's arbitrary. Okay. And I'll just give you one quick example of one such paper for uric acid. Otherwise, you're just going to have to take my word for it. But in this paper, they show that uric acid above 5.38, and that was their cutoff, was adversely associated with, and look at this, body mass index, waist circumference, waist to hip ratio, HDL, LDL, sorry, total in HDL, apolipoprotein A, systolic, diastolic blood pressure, pulse pressure, and it goes on and on. So you can see that just in a single paper, and I know that's not a lot, but there's more papers that I've been through. I've spent the past 20 years, and I continue to still look at papers. I continue to look to see if there's a better reference range for uric acid based on the literature, checking in every 6 months or so. Anyhow, based on that, first and foremost, the literature is really clear that uric acid should be stratified into men and women. There should be a reference range for men and women separate for uric acid. Okay, it's a very distinct difference. And secondly, you can see that, so here's 5.38, and you start to see that in this stratified it too, but in men, kind of around that range goes up. All right, so a summary, once again, high uric acid, it's an exogenous antioxidant. As long as there's vitamin C, it's acting as an antioxidant, and it's probably a good thing temporarily. But if uric acid is low, then that may be an indication that there's extreme severe oxidative stress. And you saw the papers, the lower the uric acid, the worse the prognosis of ALS and myasthenia gravis and a whole host of things. That's really what we're looking for, okay? So that's uric acid. Then we got two more. We're gonna talk about GGT and bilirubin. GGT is one of my favorite markers, and that's because of all the things that it can indicate, yet it's a marker that for some reason is left off panels. I realize not in Evexia panels, but in conventional medicine, they don't run it very often. And that's because most conventional practitioners, doctors, and otherwise, nutritionists, dietitians, say that it's elevated usually with alcohol consumption and maybe if there's biliary tree obstruction. And that's kind of about it, but we're gonna change that narrative. So GGT is primarily in the liver, kidney, and the pancreas. It's also associated with the biliary tree coming out of the liver. It is associated with alcohol consumption, but it's present in cell membranes itself. This is why it's a marker of cell damage, because it's in the cell membrane itself. And if the cell is spilling out or apart, then GGT is going to be released. It's in the cell membrane, however, now look at the name, gamma-glutamyl transferase. It's transferring amino acids from inside to outside of the cell in order to make glutathione, okay, which is what it says here. So, and I'll take a step back for here too. So it was introduced to clinical laboratories a half century ago. Now, some of us here, not mentioning any names, are half century old. And so, and if you don't think that you're old, being a half century old, which I don't think you should, that's not that long ago. Okay, it's within some of our memories. That's not that long ago. Insulin's only 100 years old. I'll give you, here's another little tip. So the second discovered biochemical pathway about 100 years ago was the pentose phosphate pathway, otherwise known as the hexose monophosphate chain. 100 years, extracellular pathway, every cell of the body. Do you know that within the past 5 years only, we've been studying it for 100, they said, it turns out that humans can synthesize erythritol. We didn't know that before, and it does it in the pentose phosphate pathway. So we've been looking at this thing. That'd be like looking at your spouse for 100 years, and then all of a sudden being like, you have a freckle there. And it's been there the whole time, but we didn't see it. 100 years of staring, and we didn't see it. Okay, so if something's 50 years old, if redox biology and our understanding of it is 20 years old, like we don't know that much about this stuff. Again, if we've been wrong before, what makes us think that we're so right now? We're just doing the best we can, using the best evidence we can. So anyhow, so it's new, and so we're still learning more about it. That's the whole point. Recognized as a biomarker of liver injury and alcohol consumption. I mentioned that. More recently, suggested to be a biomarker of the transition across the disease spectrum, the way that we looked at cholesterol a few decades ago. Here's a quick graphic of it. Here it is, gamma-glutamyl transpeptidase right here. It's taking an amino acid from outside of a cell, and it's bringing inside of the cell. And depending on the amino acid and how it can convert it, it can turn it into one of the amino acids responsible for the glutathione synthesis pathway. Now that is interesting. It's inside the membrane, and it's very much involved in the synthesis of glutathione. So is there some implications of GGT and glutathione? Well, let's look at the utility of GGT first. Number one, here's a paper looking at 35 studies and almost 600,000 people, and notice the terminology. Now, this is all out of the paper, but I'm highlighting this here. GGT, even at physiological levels, what that means is within the normal reference range, was associated with increased all-cause mortality, cardiovascular mortality, and might be associated with cancer-related mortality in the general population. Same thing in this paper. Serum GGT activity, even high normal values within the reference range, is associated with an increased risk of, again, all sorts of different diseases. So here's a paper that's hypothesizing that GGT is a marker of glutathione depletion in the liver. Now this becomes awesome because if we see somebody with a high normal GGT, and we need to know who should get glutathione support and who shouldn't, this is our most likely marker, and I have more papers to show you on this, most likely marker to be used for, do you need glutathione or not? Do you need glutathione support or do you not? Also notice they say that elevations in GGT reflect increased exposure to organic xenobiotics because many of these are detoxified, conjugated, or biodetoxified in glutathione conjugation, phase 2. So glutathione conjugation, phase 2, is getting used up if there's too many xenobiotics. So they're saying GGT is a marker of hepatic glutathione depletion, possibly because of environmental pollutants, but possibly because of other things as well. And they note that GGT has been steadily going up over the years. Well, so too have xenobiotics. So they say, well, what's the correlation? And they go on to say that we suspect this may be indicative of increased exposure to environmental xenobiotics, especially persistent organic pollutants, as well as increased total body burden. Now, we'll come back to that paper in a second. This paper was showing that GGT might actually have biological activity. It's not just an inert enzyme that's found within the cell membranes, that it may actually be, like I said, may have biological activity. So back to this same paper, they were saying that GGT is a stronger predictor of disease risk than things like hemoglobin A1C and lipids and CRP and all these markers that we look at for disease, but GGT might be a better marker for disease states. In fact, they suggest that serum ferritin levels, and looking at that, suggest a link to exposure to environmental and endogenous toxins resulting in oxidative and nitrosative stress. So that's what we're talking about, okay? Like, lest we've forgotten, talking about oxidative stress. It's real, it's problematic. There's cell signaling. We can't just give antioxidants because we might mess with the cell signaling, especially in healthy populations. I've covered a lot of stuff in this period of time. So we need markers of oxidative stress. So here's GGT. Look, because of its role in the cell membrane regarding glutathione, and because environmental pollutants cause issues, most environmental pollutants, one of the biggest causes of their damage is oxidative stress. And so here's a marker, GGT, that's associated with glutathione deficiency in the liver because of glutathione conjugation in phase 2, because of exposure to xenobiotics. You guys see how all this works together? So you're about to see it, but GGT in the high normal range is your marker for who needs glutathione or not. Otherwise, you're just guessing. Pyroglutamic acid, I showed you, that can vary. Okay. GGT, once again, is an early predictive marker, and we want early predictive markers, don't we? We don't want to know when it's too late. For atherosclerosis, heart failure, arterial stiffness, plaque, gestational diabetes, various liver diseases, and so much more. We need to look at GGT really carefully. I'll show you an optimal reference range for men and women in just a second. The same paper, low antioxidant defenses are also correlated with elevated GGT, particularly reduced levels of glutathione. GGT is a likely indicator of the depleted supply of glutathione, especially in the liver, which leads to a cascade of problems related to increased oxidative stress. This is a relatively newer paper, and check this out. This I was leading up to this. Sorry. GGT is a long sought biomarker. You know what they're saying there? We have been looking for a biomarker that can help us with, what do they say? Redox status. GGT is a long sought biomarker of redox status. I'm not making this stuff up. GGT in blood circulation is proposed to modulate oxidation reduction redox, which we've kind of been over, within the cells and their surroundings. Thus, circulating GGT activity might be an ideal candidate for redox biomarkers. Fantastic. Circulating GGT was a long-sought biomarker of the redox status of different illnesses and would be a valuable tool in, here you go, this is what we do clinically, you guys, monitoring oxidative stress and antioxidant stresses at the whole body level to guide the treatment. Can I put that another way? GGT is an evidence-based, I'll show you optimal reference ranges in a second, evidence-based in the literature marker suggestive of glutathione depletion in the liver because of phase 2 conjugation, maybe xenobiotic exposure because it causes oxidative stress. And they're saying here to be able to monitor oxidative and antioxidative stresses at the whole body guide to treatment. So it can tell us who needs glutathione support and who doesn't. And when we give that, should see a change in GGT. Man. So once again, I'm not going to show you the papers in the interest of time, but men and women, GGT should have a stratified men and women reference range, although it's slightly different, but a few points can make a difference. That's based on a number of different papers. Anyhow, to take that for what it is. So here's proof of concept. In this textbook, they took type 2 diabetics, and they took their GGT levels, and they gave them 1,800 milligrams of N-acetylcysteine a day, divided doses for 12 weeks. And notice that GGT came down. What did they give? Glutathione support. Now this next one might be a little bit interesting. However, when you consider where GGT is found within the cell membrane, what is the cell membrane? Phosphobilipid layer, right? Phospholipid bilayer. If we have an antioxidant that might be good at fat-soluble oxidative stress, then perhaps this GGT will be impacted as well. It turns out ubiquinol, CoQ10, the dose they used here, I believe, was 150 milligrams per day. Check this out too. So here's GGT. They gave CoQ10 for a little bit, about 150 milligrams, and it too came down. Okay, so 2 evidence-based strategies. If you see high normal GGT, there's 2 things that you can give based on the scientific literature, not in a petri dish, not in mice, not injected, human clinical trials that you can help to deal with some of the oxidative stress that's likely causing GGT to be slightly elevated. And last but not least, bilirubin is pretty awesome too, so we'll cover this. I think we're all doing all right, yeah? All right. Bilirubin is kind of cool. Most of us consider bilirubin byproduct breakdown of heme metabolism, something to do with the bile, maybe makes poop a little bit browner and urobilinogen or whatever. But let's take a look at it. It's a byproduct of red blood cell breakdown. There's 2 different kinds, conjugated and unconjugated, direct and indirect. We're not going to talk about that now, but if you run those, you can kind of decide where the problem is if bilirubin's high. But we're not talking about high bilirubin. In fact, we're going to talk about low bilirubin. Normally, indirect bilirubin is approximately about 70 to 85% of total bilirubin, 50% is more direct. This is not important for what we're talking about now. It's a major component of bile, gives it its green pigmentation. I always listen, biochemistry, physiology, incredibly important. Here's here's heme oxygenase, you require iron to do this, turns into biliverdin. And then here's what's important. Biliverdin reductase, if you notice here, is using up things like NADPH, one of the strongest reducing agents that we have via the pentose phosphate pathway, to make bilirubin. Now, I'll put it this way, and you don't have to answer this, but is there a molecular structural difference between bilirubin and biliverdin? And the answer should be yes. Those don't look the same, do they? So here, when a lab runs the blood chemistry and is looking for bilirubin, if in a second I'll show this to you, when it gets used up as an antioxidant, it's a very potent antioxidant. When it gets used up, it turns back into biliverdin. So it's like hide and seek. So when the lab is looking for bilirubin, if it became biliverdin again, it's not going to see it, and bilirubin is going to be low. So when bilirubin is being used as an antioxidant, it goes into biliverdin and it shows up as low, which is to say low bilirubin is a marker of oxidative stress. What kind of oxidative stress? I'll show you in a second. It also functions as an antioxidant and may be decreased by oxidative stress. It appears to be the most potent against lipid peroxides, fat-soluble oxidative stress. Glutathione is water-soluble. So GGT, this is where this gets great. GGT is a marker of water-soluble oxidative stress, specifically glutathione, it seems, although CoQ10 apparently can help with that. Uric acid is also a water-soluble antioxidant, but bilirubin is a fat-soluble antioxidant. Why the heck do we need anything else as our screening test using markers that are already on the lab that we should be running on our patients in the first place? Because of this, low bilirubin has been associated with an increased risk of cardiovascular diseases from all-cause mortality and a whole bunch of different causes of mortality. And if I may, you guys, let me just tell you a quick story. I remember I'll never forget, I was in the Atlanta airport. I was waiting for my flight. I was on my phone. I was looking up markers because that's just what I do. I was looking up markers and I found that I was taught there's no such thing as low bilirubin. Here's the functional high end and all this stuff. What's the low end? No, there's no such thing. And I looked at these papers and you guys, this is when sometimes you have things happen that you're like, you know what? I can't trust anything anymore. I was told that there's no such thing as low bilirubin. I will show you one paper of many that suggests if it's 0.4 or below, it is an increased risk of all-cause mortality and a whole bunch of bad things. Yet I was taught in the functional medicine industry, there's no such thing as low bilirubin. Bilirubin may also increase insulin sensitivity and protect against future diabetes. That's not more. I'll even show you more. All right. So check this out. So here's biliverdin, here's bilirubin, here's bilirubin reductase, here's that heme oxygenase, and look at this, cell membrane, lipophilic, fat-loving reactive oxygen species. When bilirubin gives its electrons, becomes biliverdin. If it's biliverdin, the lab's not running that. It's looking for bilirubin. So if bilirubin's low, it's because it's being used up for oxidative stress. This one basically says it all. Look what bilirubin protects against: endothelial dysfunction, vascular smooth muscle proliferation, hypertension, endothelial damage, and on and all-cause mortality. Bilirubin is a powerful, potent, endogenous, fat-soluble antioxidant. More potent probably than any of the ones that we can take. So here too is just a number of papers. Bilirubin is a protective factor of rheumatoid arthritis. The lower the bilirubin, the worse the rheumatoid arthritis. High bilirubin is associated with a lower risk of renal insufficiency. That's a good thing. More bilirubin is good. Serum bilirubin is inversely associated with alcoholic liver disease, non-alcoholic. Low bilirubin, high non-alcoholic fatty liver disease. Low bilirubin, increased risk for type 2 diabetes. Low bilirubin, this paper and another one, I believe, yep, worse blood flow. Same deal, worse blood flow, more hypertension with low bilirubin than high. Guys, they all say the same thing. Low bilirubin is a problem. How low? I'll show you in just a second. So this is a relatively newer paper. Look at this. I have to say this. Bilirubin, which is considered the most potent endogenous antioxidant. Now, I've heard in this industry, glutathione is the most potent, maybe intracellular. But you guys, uric acid, the most abundant antioxidant. Bilirubin, the most potent endogenous antioxidant. The body makes these amazing things. And when we look on a lab and it's telling us something, low uric acid, low bilirubin, high normal GGT, it's telling us something. Furthermore, bilirubin, look at this, has potent immunosuppressive activities. So what are the correlations between this and possible infections? What are the correlations between this and autoimmunity? With the potential to inhibit low-grade inflammation. Now let's put this all together. If bilirubin is low and it has the ability to inhibit low-grade inflammation, and it's not because it's low, that's why low bilirubin is associated probably with all those different things that we just looked at. Serum bilirubin is closely associated with markers of oxidative stress, inflammation, and healthy controls in patients with atherosclerosis. And here's one paper I was telling you about. Very clearly, there's a higher risk of all-cause mortality, cardiovascular mortality, when bilirubin dips below 0.5. So 0.4 and below is the reference range. Okay, based on that, 0.4 and below is low, and like I said. So now what do you do about bilirubin if it's low? Now, I'm showing you one paper here, okay? There are a number of papers looking at infant or neonatal jaundice and giving either CoQ10 or vitamin E, both fat-soluble vitamins, to help lower bilirubin in these infants that have jaundice. Now think about this. I just said, what if we have low bilirubin? Well, if low bilirubin, okay, ready? If bilirubin is low because it's acting as a fat-soluble antioxidant, maybe we need more fat-soluble antioxidants to help bilirubin out. Now, in this case, when it's high and they give, why would bilirubin come down if they give vitamin E in one paper or CoQ10 in this paper in order to bring it down, or zinc in another paper, which is related to heme oxygenase? Why would it bring it down? Maybe because there was oxidative stress, fat-soluble oxidative stress, and the body was trying to make more bilirubin to combat it, but by giving exogenous versions of it, that these infants had their bilirubin come down. All right. If you eat more fruits and vegetables, is associated with higher bilirubin levels. And here, if exercise increases bilirubin levels. So you have somebody with low bilirubin and you want to increase it. This paper was super cool because it told you exactly how much, it was postmenopausal women, how much exercise, how many calories you needed to burn at 50% of your aerobic capacity per week. You take 12 kilocalories, you just take 12 times the kilograms that somebody weighs. Let's just make it somebody heavy, like 100 kilograms times 12 will be 1,200 calories per week of cardiovascular exercise at 50% intensity will increase bilirubin. Okay, so there you go. Lastly, and I have a big asterisk for this, curcuminoids, flavonoids, green tea extract, soy extract, caffeic acid, resveratrol, natural coumarins may induce the expression of heme oxygenase 1, which, if you remember, was what turned heme into biliverdin. But big asterisks on this. These have only been done in cell culture studies. I have not seen any papers that suggest that any of these things increase bilirubin in any human clinical trials, and thus, if you use it, it's totally experimental. Okay. Lastly, and not leastly, and here's where we're wrapping it up. I have about 6 more slides. Thanks for hanging in there. So what I just showed you was oxidative stress, once again, is real associated with different kind of conditions and diseases. So we want to test it. Testing it leaves a lot to be desired. When you look at these papers written by these really smart people who've been studying this for years, looking at the scientific literature themselves and talking about clinically assessing oxidative stress, damage, enzymes, or reactive species, leaves a lot to be desired and has been disappointing. So then we think, well, we'll just give antioxidants. According to the literature, maybe not a great idea because oxidative stress, or let's just call them reactive species, act as signaling molecules. And as I showed you with selenium, just by giving something, we might be actually messing up that signaling system and causing more problems than we're actually contributing to. So then the question becomes, well, how the heck can we know who needs something and who doesn't? And I've shown you 3 markers, uric acid, GGT, and bilirubin, that according to the scientific literature, as well as the optimal reference ranges that I showed you, we can use, including some specific interventions with doses, even including an exercise dose, that we can use in order to evaluate potential oxidative stress, water-soluble, glutathione-related, and fat-soluble. And then we can run additional markers if we want to, but I'm telling you, we have them on these panels. But if that wasn't enough, what I want to show you is combining these markers together, which is just the icing on the cake. So here we have low total bilirubin right, oxidative stress, and high GGT, oxidative stress, were concomitantly associated with atherosclerosis in Korean men. So that's two oxidative stress markers in the direction we were just talking about. This one's pretty cool. So look closely. So these first four markers here are markers of oxidative stress. This marker, this PERSA, is a marker of sort of antioxidant. And here's bilirubin, uric acid, and vitamin E. And when you look at this, who had the higher oxidative stress? The Italians, higher numbers, or the Czechs? And the Italians did. So if the Italians, and I'm not saying anything against Italians or Czechs, doesn't matter. The Italians, for whatever reason, had higher oxidative stress markers. Well, check this out. They had lower bilirubin, marker of oxidative stress in the Czech group. They had lower uric acid, marker of oxidative stress than the Czech group. And they didn't have, they had slightly, vitamin E wasn't statistically significant. There we go, bilirubin and uric acid tracked just the way that we said it did. Once again, this one is using LDL particle size. And what they found was a significant inverse correlation, ready? This is great, between mean LDL particles and GGT. The smaller the LDL particle, the worse the problem, right? But that was inversely correlated with GGT, a marker of oxidative stress. But look at this, a significant positive correlation was between mean LDL particle size and bilirubin. So that means, remember, small particles are bad. According to this paper, small LDL particle size was associated with a higher GGT, oxidative stress, and a lower bilirubin, also oxidative stress. You guys, I can't make this stuff up. This works. A couple newer papers. Total bilirubin, once again, and GGT, ready, have an interaction effect on the risk of incident metabolic syndrome. And what they suggest was the simultaneous presence of high bilirubin, which is not oxidative stress, and low GGT, which is not oxidative stress, may be associated with a lower incidence of metabolic syndrome. And then finally, listen, I'll be real honest about this. I only read the abstract. This was just published like days ago, okay? Well, it was published in October, it was just printed. So I just read the abstract. I usually read the whole thing. But check this out. So they were looking at this Life's Essential 8, which is a way of looking at cardiovascular disease, and this what they called phenotypic aging. But what I wanted to point out was they revealed that oxidative stress biomarkers, GGT, bilirubin, and uric acid contributed to this. I mean, I can't make this up. The three stinking markers that I have been studying for years in this brand new paper, they said that revealed that these oxidative stress markers, okay, so, man, not bad. Oxidative stress exists and is associated with a whole bunch of chronic conditions. However, redox biology is super complex and assessing it is equally complex and has proven to be inaccurate. And I suggest that we don't do that very much because it's not as accurate as we think that it is. Also, randomly suggesting antioxidants appears irresponsible, ineffective, and even potentially dangerous. I use the example of selenium, although there are others. Thankfully, we have three evidence-based, inexpensive markers informed by the scientific literature to guide us who might have, number one, oxidative stress, two, who could benefit from additional antioxidants, and three, to inexpensively, on a blood chemistry, track their progress. Bam. So listen, if you guys are into QR codes, you can use your phone on that. If you don't, this is the website here, metabolicfitnesspro.com. If you want to join the critical thinker, practitioner, truly evidence-based, again, not petri dish studies or mouse studies, you can head on over there and see what we're up to and learn more from us. So Joanne, you still there? That was kind of a lot. I told you. I warned you ahead of.
Wonderful. Thank you so much, Dr. Walsh. That was just a great, excellent presentation. I'm going to let you take just a little breather, a couple questions. I'm going to field through some of these questions. And of course, we always love Dr. Wayne Sedano on board with any feedback on this presentation and a few questions. So Dr. Sedano, I was just going to ask you, aside from antioxidant effects, does bilirubin have any other beneficial effects in the body?
Yeah, hi, Joanne. Doc, thank you so much. It's great. Just one thing before I answer that, Joanne, if anybody wants to look up this word, everybody have to look up the word hormesis. And I know Doc knows what I'm talking about. It's a wonderful word to use to get an idea of that something beneficial can get skewed and become toxic, even a nutrient. So that's kind of something that I stress with my students as well. As far as bilirubin, Doc kind of mentioned that as bilirubin can be an antioxidant, immunomodulatory. Little side note, and Doc, if you want to chime in on that, it's my understanding that bilirubin can actually block interleukin 6, and it can suppress tumor necrosis factor alpha, among other things. So it's pretty powerful.
Yeah, it's beyond powerful. I mean, and it's immunomodulatory, inflammation inhibitory effects. Yeah,
But,
which is
Doc,
why, and then not surprising to see low bilirubin is associated. It's not so high bilirubin. You think of liver issues or Gilbert syndrome or some of those types of things. Interestingly, I mean, if you really want to learn about bilirubin, look at Gilbert's studies because they have tremendous antioxidant capacity. And it's thought that because they have other issues, right? Because they can't go through glucuronidation as well. That's not a problem for them. That antioxidant capacity, because they have so much bilirubin, is somewhat protective at a certain level.
Yeah, thanks. And Doc, just want to pick your brain on one thing. You're heavy into the research, and that has to do with albumin. Albumin as a trap for antioxidants, and I know we're talking about the other markers, but I know that having low albumin can create a problem because it's a negative acute phase reactant. Have you done studies with that, or can you just?
Oh, yeah, 1000%. Yeah, no, listen. So, I mean, true story. Albumin was okay. So I'll keep this short. So I learned functional blood chemistry. I'm not mentioning any names, but I learned it in the industry, 15 years ago or so. And I used it, but the ranges were kind of I don't want to say obscure, but I didn't know where they came from. I was questioning on them in practice, and I remember looking at a blood chemistry. This is a true story. This is albumin. I have kind of a love story with albumin because it's what tossed me down this road. And I was looking at a lab. I was like, what the heck is albumin in the first place? I went to naturopathic school. I learned about it somewhere, but I was like, isn't that egg whites? I mean, what is albumin doing on this lab? And so I studied albumin by itself to death. And then I learned, when it's made, where it's made, how much it's made, synthetic rates, how it's excreted, half-life, binding capacities, negative acute phase reactant, like I said. So I know quite a bit about it. Yeah, listen, so when you look at the literature, it's a lot higher than what's taught about in this industry. But when you start to go down below around 4.4, it's a marker. It's either a marker of liver damage because that's where it's being synthesized, right? But if you look around at the rest of the panel, if the liver's not making albumin well, it's not going to be doing other things as well, like cholesterol, like BUN, right? So you can look around at the rest of the panel. If those are normal, the only other thing that albumin can be really is kidney disease because it's such a small protein, it's being lost out of the kidneys. But again, if it's that severe kidney disease, you're going to see some evidence on the panel somewhere. So the last thing it can be is inflammation. It's just low albumin is a marker of inflammation, hands down. It's a negative acute phase reactant. Interestingly, it's the main binding protein that fatty acids bind it onto for transport. Calcium binds onto for transport. And even weakly some hormones. So you can start to see calcium issues and a variety of other things just merely when albumin goes down.
Yeah, thanks, Doc. Yeah, it's kind of like the stepchild there, the albumin. It can tell us a lot on lab as well. Thank you.
Great. Here's one on here. I just want to confirm this from a clinician. Do you need to be testing oxidizing LDL or just working through the biomarkers we're talking through?
It's a super good question. That is one of the markers in question as to its accuracy, because what it is, remember, if you go back to that one paper, it says that oxidative stress is a dynamic concept, yet we're testing these static biomarkers. I once thought that oxidized LDL is a great marker because that's the one that gets through the endothelium and the macrophages and the foam cells and causes the damage, right? But if you go back to some of those earlier slides, that they can be subject to repair. There might be some intra-individual variance to these things, depending. And so similar to that pyroglutamic acid that varied quite a bit, I don't think it's as solid. Okay, I'll put it this way. I don't think oxidized LDL is as solid of a marker as LDL particle size, because LDL particle size, if you have the smaller, dense LDL particles, regardless if they're oxidized or not, are more potential damage to the vascular wall than is like just say oxidized LDL. So in my humble opinion, and listen, I told people at the beginning, don't listen to me. Look at the evidence. That's totally cool. Me, I use these three. That's all I use. I don't, based on the evidence, I don't think we need anything else personally. Okay, sorry, a quick caveat. But if it's on a lab, you look at it. You look, I mean, if it's there, you look at it. So, but I personally don't see a need to run.
Could you repeat the name of the article that has just been published and you only read an abstract?
Oh, yeah. So I could go back to that, but it was, oh, heck, I'll just go back. I think it was this one. Oxidative stress factor mediate the association between life's essential 8 and accelerated phenotypic aging using some NHANES data. And, so these things here, this pheno-age excel and this LE8, those are things, but I came across this because they use the three markers I was talking about.
Thanks, Dr. Walsh.
Yep.
Let's just go with one or two more. A couple of these are pretty complicated. We will definitely reach around and give you answers on this in the next couple days or so. Would you recommend measuring 24-hour urine for uric acid levels or body fluids? Is there a benefit to ordering both? Is there a benefit for knowing total and direct bilirubin levels, or is just knowing one enough information?
Great question. There's a few there. Okay. So a 24-hour uric acid test would only be a follow-up, and that's if somebody thought there was a problem in the first place. So, just as a screening test, I wouldn't bother. On the other hand, if you're going to do a 24-hour urine test, you may as well throw in some other things like iodine, and just if someone is going to collect, you wouldn't just collect it for that. You'd say, let's do a 24-hour urine test and collect a number of things to look for potential issues that you suspected based on signs, symptoms, history, and blood work. I am of the opinion that if they're already doing bilirubin, do indirect, or conjugated, unconjugated, because the needle's already in the arm. They're already looking at bilirubin. They just have to look at the fractionated versions of it. And so, yes, I think, because if there's an issue, you don't have to send them back. You already have the lab. Versus the 24-hour urine test, you'd have to send them back for that anyway. So big yes to indirect and direct on just the standard lab, personally.
Thank you. All right, we'll go with this last question. This goes back really early on in the presentation. Can Dr. Walsh clarify what he said about hair tissue mineral analysis not being appropriate at the individual level, but helpful for assessing toxicity at the population level?
Yeah, so I'm liable to have, like organic tomatoes thrown at me for saying this. I have a whole, I have a whole presentation just on this subject. And again, I'll just give some real context to this. I was trained deeply in hair tissue mineral analysis about 20 years ago, both basic and advanced courses. I bought every book on the subject at the time. I got, because it's fascinating subject. Minerals are fascinating. Their interactions are fascinating. Their ratios are fascinating. So I'm not just coming out. I did it. I did it on myself. I did it on clients for a while. So I'm familiar with it. I'm familiar with the labs. I'm familiar with all of it. The literature, however, I will tell you, is really, really clear on this. There's a bunch of issues with it, but the literature is clear that that particular type of test, and there's other ones too, that are really good at the population level because you're taking averages. And so some might, let's just say selenium. Some might have high selenium, some might have low selenium, but if you're doing it on 1,000 people or 10,000 people, you'll get an idea if a population in a specific geographic location or a certain ethnicity or whatever it is tends to have issues with that. Now remember, that's going to be a bell curve. You're going to have some pretty extreme outliers when it comes to that. But on the individual level in a clinical practice, it does not pan out. It does. I wish it did, because I mean, what an amazing test. But according to, I have currently 82 papers on hair tissue mineral analysis, mostly on humans. I've looked at some on horses that were really well done. And I wish I could say it was a good test, but it doesn't hold much water in what I've seen.
Dr. Sedano, aside from these, the three tests, uric acid, GGT, and bilirubin, are there any other regular lab tests that is associated with oxidative stress?
Well, yeah, we had talked about looking at the regular lab tests. That's why I was focusing on the albumin that Doc had explained quite well. Again, being a negative acute phase reactant, that may add to that mix as well.
Excellent. All right, Dr. Walsh, you want to move on to the next slide, and
Yeah.
we can just finish up for the evening.
Yeah, to Dr. Sedano's, something he might find interesting, however, is albumin in the case of inflammation, it's an antioxidant protein, can become a pro-oxidant. I have a couple papers on that, but it actually becomes a pro-oxidant. And so during inflammation, it goes through what's called a conformational change. And so when it does that, it goes from being this happy, positive antioxidant albumin to this, evil pro-oxidant albumin, probably for a purpose. And it's kind of like HDL. HDL is an antioxidant and a pro-oxidant, and it's not always good. So these things, when some of this physiology happens, it's no longer a marker of what we thought it was. Anyhow, yeah, here's the next slide.
Oh, so these would be some other suggested Avexia wellness panels or some of the other options for testing for oxidative stress. We do have several of the Avexia panels. Of course, the slide here, Genova Diagnostics, Doctor's Data, and LabCorp. And we have gone over the questions, and anyone that we haven't been able to address, we will circle around with you on that. I think just the last couple slides, we'll just kind of go over how to place any orders. So is there another slide at all? There you go. Just a reminder, Dr. Sedano's on. He is our Ask the Doctor. Any help with lab interpretation, questions on clinical conditions, on the left-hand side of your portal, feel free to ask Dr. Sedano anything, review results, and he's fabulous with his answers and working with all of our practitioners. And next slide. So now that we've learned about oxidative stress, just want to review how to order any testing mentioned in the presentation before we conclude this webinar. You will log into your Avexia account and go to Avexia link ordering. Of course, register your patient or find your patient. And then from there, you can either go to specialty testing if you are looking at Genova or Doctor's Data, or just through LabCorp. So each of those tests are very inexpensive. I mean, $4, $3 for these. So feel free to add them on in a panel if we can help you. Obviously, reach out to our client services team. But you'll just find the tests available, add it to the shopping cart, and just preview your order and check out. As always, we can bill the clinician, or orders can be assigned to patients to pay. And I think that might be it. So for any questions or concerns, you may contact Avexia Diagnostics by email at info@avexiadiagnostics.com, by phone 5 days a week. Live chat is also available. We are here 8 a.m. to 8 p.m. Eastern Standard Time. Thank you so much, Dr. Walsh and Dr. Sedano, for this informative presentation and all of your feedback and answers. A recording of this webinar will be available by email to all of you in the next few days. Thank you again for joining us for this webinar event. Until next time, from everyone at Avexia Diagnostics, stay healthy, stay safe, and we wish you all the best on your pathway to wellness. Good night, everyone.